better not think about. Where does last night's dinner go when we flush it down the drain? While you may already be grossed out just thinking about it, this question leads way to a significant subset of civil engineering and a massive amount of public funding. Just like all dogs go to heaven, all drains in a city lead to a wastewater treatment plant where that wastewater gets turned back into water that we can drink. Now, you may be thinking that you'd rather just let bygones be bygones and not think about this nasty part of real life. But here's the thing. Chances are you've drunk water that was waste at some point, so you might want to take some time to understand this engineering process that makes dirty water clean. Here's where it starts. The toilet. Once you're done doing your business and flush that magical handle, your waste ends up at the inlet of one pretty interesting place, a wastewater treatment plant. Why is this place so interesting? Because it takes arguably one of the most disgusting substances in the world and turns it back into something that is essential to all life. Flushing just your toilet at halftime may not seem like a big deal, but when you couple it with thousands, if not millions, of others doing the same, it can result in some pretty high sewage flow rates. New York City has an array of 14 wastewater treatment plants that handle a combined 1.3 billion gallons of wastewater daily. That's enough wastewater to fill the Dead Sea with pure sewage in just 8 years. And that's just New York City. There are an estimated 14,748 treatment plants in the US alone that 76% of the USA's population relies on, according to the American Society of Civil Engineers. Understanding wastewater is crucial to understanding the critical infrastructure needed to support modern life. That brings us to the first step of the process that handles larger items in sewage, things like flushable wipes, 2x4s, toys, or even guns. You name it, and it's probably been caught in a bar screen. Bar screens are exactly what you would think. They are large vertical bars that stand at the inlet of nearly every wastewater treatment plant, designed to stop larger items from getting to the plant and hurting machinery like pumps. This first process where bar screens are used is commonly referred to as pretreatment. The sole intention of pretreatment is to remove the outliers in the sewage and make the whole mixture a little more homogeneous, or slightly less chunky. Bar screens are typically mechanically raked at certain intervals, depending upon the flow rates of the water treatment plant, although some older plants will still have more manual removal processes. Whatever is removed from the bar screens is then sent off to your average landfill or solid waste handling facility. Or, in the case of unusual items, such as guns, they're sent off to the evidence locker in a police station to be investigated. Next up is the grit chamber. Grit chambers are the next steps in the pretreatment process following bar screens. Since these bars don't catch everything, larger particles called grit still need to be removed from the sewage as it is made even more homogeneous. As the sewage flows into the grit chamber, the velocity of the rather viscous sewage is adjusted to allow for particles of sand and rock to settle out. This is needed because these particles can't be removed using chemicals, and they could potentially clog or destroy pumps later on in the process. There are 3 types of these chambers: horizontal grit chambers, aerated grit chambers, and vortex grit chambers, which all accomplish the same task using slightly different methods. Following the grit chambers, the sewage will move on to the primary treatment process, which starts with a large basin called a primary clarifier. Primary clarifiers, and clarifiers in general, function on the principle of settling velocity. This term can be defined simply as the speed at which a particle settles. For wastewater being pumped into clarifiers, it's important that the flow rate of the water being pumped in doesn't exceed the settling velocity of the particles trying to be removed. In order to accomplish this, engineers will vary the size and number of primary clarifiers in accordance with the plant's permitted sewage flow rate. This ensures that at varying flow levels, solids can settle out of primary clarifiers to the correct quantities. At this step in the process, the slightly treated wastewater, which is referred to as effluent, is free of solids larger than 10 micrometers and should be all organic matter, which will be treated further. The top layer of the clarified water flows over a weir wall and into the next basin in the process, called the aeration basin. Now begins the process of secondary treatment, the sole focus of which is to significantly degrade the biological content of the sewage. In many cases, this process starts with aeration basins. Effluent flows into the aeration basins, at the bottom of which are hundreds, if not thousands, of tiny air blowers that create bubbles through the water. The water is pumped into this tank along with something called return-activated sludge. You can think of return-activated sludge as a bunch of happy little bacteria that get to eat their favorite foods all day long. This introduction of significant amounts of bacteria along with the massive amounts of oxygen injected from the bubblers creates an environment perfect for the process of aerobic digestion. Summarized simply, it's the breakdown of organic matter along with the use of excess oxygen. Some older plants will add in another step before aeration basins referred to as biofilters or trickling filters. Found in many older plants, these filters essentially trickle the effluent over a medium like stone or plastic and allow for a film of bacteria to chow down on any organic matter in the water. This step is largely not used in newer plants due to more efficient and effective modern processes. But for plants with basins already installed, many still use them because they only benefit the treatment process in most cases. Following aeration basins, the effluent along with much of the sludge is pumped into a secondary filter or clarifier, where some of the sludge is removed and pumped back into the aeration basins as the return-activated sludge. Further settling of larger particles is also accomplished in these basins, as it is the final step of the process that will remove solids and larger biological matter. Water flows out of secondary clarifiers over a nearly identical weir wall to the primary clarifiers and moves on to the disinfection process. At this point, 85% of all organic matter is removed from the water, and the effluent should be safe to drink in most cases, although you probably wouldn't want to. Disinfection is the final step of the process and is usually accomplished in one of three ways, either through chlorine, ozone, or ultraviolet disinfection. Each process has its benefits and drawbacks, with each being used commonly throughout the wastewater treatment process across the world. Chlorine disinfects the water through chemical disinfection. Chlorine, which you can think of as concentrated bleach, is added to the effluent here to kill off any remaining bacteria and organisms still living in the water. When chlorine is added to kill off the bacteria, it then has to be removed before it can be discharged, as to not kill off anything in the discharge location. After this, the water is safe enough to discharge into a stream or lake. Ozone disinfection is another method of disinfection that involves pumping an electrical current through the water that causes oxygen molecules, O2, to disassociate and combine with a free oxygen molecule, forming O3, known as ozone. Ozone is an incredibly strong oxidant and causes microbes' cell walls to leak, rapid cell decomposition, and overall damage to cells. In other words, it kills off bacteria. The last common method uses ultraviolet light to scramble bacteria's DNA so that they cannot multiply. In UV disinfection, the bacteria in the water aren't killed, rather they're sterilized, rendering them harmless. If you were to ingest water with living microbes immediately following UV treatment, any harmful bacteria would be unable to multiply or render your body damage. Engineers choose between these methods based on a variety of factors such as flow rates, cost, and location of discharge, which brings us to the final step, effluent release. Effluent release exists in one of two forms. In most cases, the now treated water is released back into a stream or lake or other water source. In rare cases, usually in areas where water is scarce, the effluent discharge from a wastewater treatment plant can be discharged into another treatment plant directly, where it will be treated further for consumption. This is referred to as full-cycle water reuse. From a chemical perspective, the final drinking water is the same as normal treated water that flows through your pipes now, but due to the connotation of your drinking water being sewage just days before, this treatment process is normally shied away from or not heavily publicized. The entire process of wastewater treatment takes on average 24 to 36 hours from when a drop of water enters to when it leaves. Each wastewater plant will receive a permit for flow rates, chemical levels, and effluent quality, among other things, from the EPA that outlines the necessary treatment for a plant. Wastewater plant operators will make adjustments to a plant's operation and constantly measure levels to ensure proper discharge and proper treatment. Without these operators and the dirty job that they do around the clock, our sewage would always stay sewage, and sanitation in modern cities would be much, much worse. Wastewater treatment is an essential dirty job, and you can thank the 14,748 treatment plants in the US alone for not having to worry about what happens when you flush.